Good afternoon, this is Schweitzer, and we're going to do a little practice video on essentially one of our quizzes. This is usually on one of our second quizzes where we'll determine the pH of both strong and weak acids. Alright, in this situation I have three acids. They're all the same concentration, and I'll be determining the pH of each of them, and I'll be drawing a model of what each of them looks like. So this is the HNO3, and I'll just continue the beakers down as we go. First things first, HNO3, you should know, is a strong acid. It will undergo hydrolysis to produce H3O plus ions and NO3 minus ions. In this situation, I would develop an ice table, initial stoichiometric ratio end, and then this is 0.5. Water's not it's not being tracked. Keep in mind, a K equilibrium system is going to track concentrations. Either way, the water doesn't have a concentration, so it's not going to be tracked. I have none of this guy here, and this is going to go minus 0.5 down to 0, the classic limiting reactant, and this is a completion, so plus 0.5 plus 0.5, and I would just take the negative log of my H plus concentration, 0.5, and my pH is 0.3. Most students would just take this guy and plug it right into their expression at being 0.3. And H plus, NO3 minus, H plus, NO3 minus, H plus, NO3 minus. That's my neat picture. You would never see any of my original acid left behind because it's all goes to product. Alright, maximum conversion. In this situation, I'm going to do one more calculation alongside this. It's called percent ionization. This is like what fraction of your stuff ionized. And you would do your change, or your how much you changed, your stoichiometric ratio changed. So your stoichiometric ratio, often referred to as your change, over your original or your initial amount. So we had 0.5 change over the original 0.5 times 100 is 100%. That is by definition a strong acid. Let's do the next one. Okay, so I have HCN. HCN is a weak acid, hence I have a Ka value. Write out my expression, HCN plus H2O yields H3O plus Cn negative. Now, when I go through this process, again, I stress to kids that it's more different than it is complicated. First example, second example, third, they're all the same. The Ka expression for this guy is the concentration of my products, H3O plus, times the concentration of my other product, Cn negative. Make sure you include your charges there. Concentration of HCN, and again, on an AP exam, you need to definitely have brackets, which represent molarity. That's that. Initial stoichiometric ratio end, 0.5 molar. Not playing a role, okay, and then 0 and 0. I have, now in this case, a typical classic mistake would be to run this guy down to 0, but for a weak acid we have a reverse reaction. It turns out that the reverse reaction for weak acids is quite prevalent. In fact, the forward reaction is tiny compared to the reverse reaction. Hence, we end up being very reactant favored. Therefore, small K value. Okay, so I don't go to 0. I'm going to go somewhere else. I'm not going to have a limiting reactant. I'm going to lose X of this, gain X of this, and I would say that X is extremely small because I am so very much product favored. This number right here is 6.2 e to the negative 10th equals, okay, and then this fractional relationship equals 6.2 e to the negative 10th, which means that I almost exclusively have that chemical. Okay, how much of it do I have, or how much did I lose? It's 0.5 minus x. Just put those together. 0 plus x is x. 0 plus x is x. Remember, the ending is really just an addition of the first two. Okay, and then at this point, plug the equilibrium values into your expression. I get x squared, or I'll jump the gun here, is x times x, and then it's 0.5 minus x. Now, I'm going to show two ways to solve this problem. One is a tad longer than the other one, and although not much. So let's do the longhand version first. I want to algebraically solve for x. So I have 6.2 e to the negative 10th equals x squared over 0.5 minus x. Multiply by the bottom to get it off the bottom. I get 6.2 e to the negative 10th times 0.5 minus x equals x squared. I'm going to distribute here. Okay, half of 6.2 is 3.1 e to the negative 10th minus 6.2 e to the negative 10th and equals x squared. And this would be x here. Alright, and then I move it all over. I get, in this case, x squared plus 6.2 e to the negative 10th x plus 3.1 e to the negative 10th and equals 0. This is just your typical quadratic formula. I'm not going to walk through how to do a quadratic formula. In fact, I would suggest you just get yourself a program solver in your calculator called quad form or whatever. The A component is 1. The B component is 6.2 e to the negative 10th. And the C component is 3.1 e to the negative 10th. And your journal error. Let's see the calculators. Okay, so in this case, make sure you do your math correct. Add that over, and this guy should be a negative as I subtracted over 3.1, and it did not like that, and that's the reason why. Alright, so again, 1 is my first value, B is 6.2 e to the negative 10th, and my last component is negative 3.1 e to the negative 10th, and I get, okay, now when you quad form, you always get two forms of an answer. One makes sense, one doesn't. We're not going to lose a negative amount, so we're going to be having a positive number here, and therefore it is the x component equals 1.76 e to the negative 5th, and they end up being very close, both numbers, and it's negative 5th, in case you can't see that. That equals x, which is the amount you will lose of that guy and gain of that guy, and that's what I want. So the negative log of 1.76 e to the negative 5th equals the pH. So negative log, that answer equals negative log 1.76 e to the negative 5th equals 4.75 is my pH. Now notice I still had the same original amount, and the strong acid gave me a 0.3 pH. Now I only have 4.76, not nearly as acidic. Alright, let's try our third example here. Okay, now 0.5 molar. Actually, I want to do this the other way here. I forgot about this. So we're going to use an alternate method. Okay, let's see how close we are. I got this alternate method just uses a bit of a shortcut. So I have 6.2 0.2 e to the negative 10th equals x squared over 0.5. Okay, now what they do here, the shortcut is that they're going to eliminate this minus x. X is tiny. X is 1.76 e to the negative 5th. So we're saying that that number compared to 0.5 is essentially 0.5. Run the math through that way, and you'll avoid a quadratic. This multiply up is 3.1 e to the negative 10th equals x squared. Square root both sides, and x equals the square root of 3.1 e to the negative 10th, and you get 1.76 e to the negative 5th. Very well, in this case, it is exactly the same. Well, it's not, and if you drag that decimal on, you'll see it's slightly different. But if I take the negative log of that answer, and because I didn't keep track of all my decimals, this pH ends up being exactly the same. All right, so the shortcut rule worked effectively there. In fact, the smaller the Ka value, the more or the better that shortcut works. The general rule of thumb is as long as this guy is negative 4th or smaller, it's within range to use the shortcut rule. Now our next guy is 0.5 molar HClO2. Now this guy has a Ka value that is 0.00011. Correction, just to make sure we're correct, it's just 0.011, so it's much larger than the other one, 1.1 e to the negative 2nd. That's the Ka value. So it's actually a pretty big Ka value, and technically would not qualify for our shortcut rule. All right? And we could do it both ways, and you're just going to see a larger discrepancy between the two. Either way, so let's do this here. We have HClO2 plus H2O yields H3O plus ClO2 minus. Initial stoichiometric ratio and 0.011, not playing a role, 0, 0, minus x plus x. And you notice it's always the same. 0.011 minus x, x, and x. All right, the Ka expression for this guy equals concentration of H3O plus, concentration of ClO2 minus, concentration of HClO2. That's, again, standard. Plug it in. I get 1.1 e to the negative 2nd equals x squared over 0.011. Now I can't use my shortcut rule here because the x value is too big. All right, so I'm going to go ahead and in this example use my quadratic once more. I'm going to go move it up here. I got 1.1 0.01. Let's go with that to get out of scientific notation times. All right, and then I'm going to back up here because I made a mistake. I'm going to eliminate my initial concentration. I plug that in there. It's 0.5. That's what we used for all of our examples, and that is what I want to continue using for these guys. All right, just so we're all comparable concentrations. So it's that guy times 0.5 minus x. All of them be the same concentration equals x squared. Multiply over half of 0.011 times 0.5 is 0.0055 minus 0.011x equals x squared. Okay, at that point, let's run our quadratic. 0 equals x squared plus 0.011x minus 0.0055. Plug it into your calculator, and we get 1.011 negative 0.0055, and we get x equaling 0.068. Now again, 0.068 is much smaller than 0.5, but we're saying that statistically or within reasonable doubt range, it's too much of 0.5 to use the shortcut rule. At that point, you take the negative log of 0.068, because that is equaling the concentration of H plus ions, and you will get the current pH, which is 1.16. So we have quite a range here, from 0.3 up to 0.47, all starting with the same concentration of H plus ions. Okay. Now, if I were to draw models of these things, the first one looks like this. The second and third one, okay, are a little bit more difficult to draw. Let's do here the percent ionization for our middle acid. Okay. Now, the middle acid, which was your HCN, again, it originated at 0.5, and so did the HClO2. So I'm doing percent ionization. So how much of it actually, what percentage of it flipped over? In this case, I got 0.068 is what moved over. That's X, essentially. So X over my initial amount is what I have. Now, you notice that in a strong, X and initial are the same, so it's 100%. The top one is 1.76 e to the negative fifth. Let's do the math here. Times 100, okay, and then we have times 100, 1.76 e to the negative fifth divided by 0.5 times 100 equals only very small amount, 0.0035%. So that means I literally would need to draw, if I'm not correct here, I could draw 1,000 of these things, and only 3 of them would be ionized. Tens, hundreds, thousands, yes. If I were, so, anyways, not much. Or 10,000 of them, and I would have 35 of them converted over. So, picture-wise, we generally just draw this as all reactants. It's just going to be HCN, HCN. I'm going to make this a little better picture. All of my acid is just going to be remaining as reactant in my picture. HCN, HCN. Okay? Now, my other guy. Okay. 0.068. I got a little bit more flipping over. 0.068 divided by 0.5 equals times 100. I have about 13%. Now, this guy is quite a bit bigger than that. So I'm getting an answer here of about 13% ionization. So I might, in this guy, draw out a few more and say, okay, I have HClO2, HClO2, and maybe H plus ClO2 minus. Now, in my picture, I'm showing 1/3, 30% of them, 33% being ionized. Not accurate. I'd only have to draw 100 of them, and I could draw 13 of them. That would be ionized. But either way, I'm going to go ahead and stop there. Good practice. Thank you very much.